The electric potential at some distance from a single point charge can be derived from the expression for its electric field. Now that we have set up the idea of electric potential, we want to apply it to something other than an electric. Now that we have set up the idea of electric potential, we want to apply it to something other than a uniform field. We've already discussed the electric field around a point charge, and we know that it is anything but uniform. We have the field radiating out from the point in all directions, but as we get further away from the point charge, the field gets weaker. So describing the strength and direction of the field depends on where you happen to be within the field. To really describe the electric field at a given distance from a point charge requires calculus, which we are not going to do. But know that the potential in the case of a single point charge is usually taken to be zero at infinity. That makes sense if you think about it. If you are an infinite distance away from the point charge, it will have no effect on you. Now, infinite in this case simply means indefinitely far away, or out of reach of the electric field at the point charge. For our purposes, we are going to define the electric potential of a point charge as a constant, k, times the magnitude of the point charge divided by the distance away from the point charge. In this case, the constant is 9.0 times 10 to the 9th Newton meters squared per Coulomb squared. So now we are no longer looking at the change in potential from one point to another, but the potential at one point. Now here's what's interesting. This is not a vector quantity. Here we can think of voltage as representing the absolute potential at a distance r from the charge q, where the voltage is zero when the distance is infinitely far away. So really what we can say is that voltage is the potential difference between r and infinity. Note that the potential near a positive charge is large and positive, and it decreases towards zero at very large distances. Similarly, the potential near a negative charge is negative and increases towards zero at large distances. Since we are not dealing with vector quantities, if you have more than one point charge within your field, all you have to do is add up the individual voltages. The electric potential will then be the sum of all of the point charges. So what is the voltage 5 centimeters away from the center of a 1 centimeter diameter metal sphere that has a negative 3 nanocoulomb static charge? We are looking for the voltage, and we know that the charge on the particle and the distance from the sphere, so this nicely fits into our equation. Nano, remember, is 10 to the negative 9th, and centa is 10 to the negative 2nd, and we find a negative 540 volts. Now say we have a Van de Graaff generator with a 25 centimeter metal sphere that produces 100 kilovolts near its surface. What excess charge resides on the sphere? In this case, we are looking for the charge, and we know the voltage and diameter of the sphere. Kilo means 1,000, so we actually have 100,000 volts being produced. The surface of the sphere is half the diameter, or the radius of the sphere, and the result is 1.39 microcoulombs of charge. So what minimum amount of work must be done by an external force to bring 3 microcoulomb charge from a great distance away to a point 50 centimeters from a positive 20 microcoulomb charge? Remember that the change in electric potential is the negative work per unit of charge. Note that here we are dealing with an external force, so the change in potential energy will be positive instead of negative. So that gives us a nice place to start. Since we are dealing with point charges, we need to find the voltage associated with each point charge. This gives us the external work required to move the charge to be the magnitude of the charge multiplied by the change in potential energy. Now remember, when we say a great distance, we are really meaning an infinite distance. So the potential energy for the initial distance will be zero. Now we have everything we need, and we find 1.08 joules of work to move that charge. So the electric potential at some distance from a single point charge can be derived from the expression for its electric field and is given by K times the magnitude of charge divided by the distance of that charge.